This is Magic 063 Differentiable Manifolds. I'm Kirill Mackenzie, and this podcast is about tangent vectors in Rn. So think first of all about vectors in R2. There are two concepts. There's the one in which you can move the vector parallel to itself and it's still the same vector. So these are called free vectors. And this corresponds to the idea that a vector has direction and length, but its actual position is not significant. It can be moved around parallel to itself. And this is quite a useful concept in some settings. But what I'm concerned with here and throughout the course is the other concept where the vector is actually bound to a particular starting point. So I'll write little x for the starting point and capital X for, well, we'll spell out in a moment what capital X is for. And these are bound vectors. And it's quite easy to, before I go on, let's represent them as little x and capital X in Rn cross Rn. And that's the set of all the bound vectors at all the points of Rn. And I'm going to anticipate slightly. We can add vectors provided that they're at the same start point. So if I have another vector here, oh, that's peculiar. Just a moment while I fix that up. So let's put the start point back in. Right, if I have another vector y at the same start point, then I could add in the standard fashion by the parallelogram rule, and that is x plus y. Whoops, x plus y. Let's make that a plus, x plus y. And you get, and you can do scalar multiplication, and you get, in fact, a vector space, which could be you get, in fact, a vector space which can be defined. The operation can be defined simply like that, with the similar formula for scalar multiplication. Okay, so I'll draw that diagram again. Start point is little x, and the actual vector is little x comma capital X, and that's an element of Rn cross Rn. And the point now is that if I've got a smooth function on the whole of Rn, or indeed justified in the neighbourhood of little x, but let's keep things simple and regard it as on the whole of Rn, then I can define the derivative of that. I can take the derivative of that, starting at x, and varying along capital X. And that's the sort of directional derivative, but most people who actually talk about directional derivatives in advanced calculus mean that the direction is a unit vector, and I don't want to do that, so I won't use that terminology, but that's still really the idea to have in the back of your mind. And by the chain rule, that's simply the partial of f with respect to x1 times capital X1 plus the partial of f with respect to x2 by capital X2. Now, if I remove the f from that equation, then what I've got is an identification of my bound vector with capital X1 partial little x1 plus capital X2 partial little x2. And that's a completely reciprocal relationship. If I write down any differential operator, actually this is not quite a differential operator, we're just talking about a specific point, but I'm speaking loosely. If we have any expression of that form, then it corresponds to a bound vector, and conversely. And addition of bound vectors at little x corresponds simply to additions of these expressions here on the right-hand side. Okay. So that's the sense, or one of the senses, in which these bound vectors are tangent vectors to R2. Now, terminology and notation, I'll use capital T for subscript little x of Rn to be the set of all these pairs starting at little x, such that capital X is in Rn. And that's a vector space, as described earlier, and we identify elements with these differential expressions. Since we're doing Rn, let's write sigma capital Xi partial Xi. Okay. And as time goes on, I'll often write capital X with the little x as a subscript. That's the more general notation. And I also want to consider all the unions, the union of all the tangent spaces. And this is actually a disjoint union because, after all, if x and y are two, small x and small y, are two different points, then these pairs cannot coincide. And so this is as a set, and later on as a manifold, is just Rn cross Rn. And if you like to think of that as R2n, well, that's okay, but actually this factorization is a good thing to keep in mind, because the two factors, the two components, really do play different roles. This is the start point. This is the start point, but the notation or terminology that we'll generally use is that that's the base point, and this will be the other one will be the fiber point. We'll get to that later on. Now, assigning a bound vector to every point of Rn constitutes a vector field on Rn. And there's some rather ambiguous notation that's pretty well universally used. So this needs to go from Rn into Rn cross Rn. Okay. And the capital X, of course, is a function of little x. But the actual map from Rn to Rn cross Rn is usually denoted by the same letter. Sometimes we'll do special notation to handle particular situations, but in general it's quite common to do it like this. And so now you should imagine the weather map, the usual picture of this, with lots of little arrows of different lengths and directions, one at each point. And that's the visual image of a vector field. And given such a thing, we can operate on smooth functions again. And this is going to be another smooth function. And at the point x, it's going to be x of x acted on f. And that, of course, is sigma capital Xi at x partial f partial xi evaluated at x. Okay. And this x sends smooth functions to smooth functions. Okay. And it certainly sends sums to sums. And scalar multiples to scalar multiples. For products, of course, by the ordinary product rule, at a point little x, what we get is the value of f at x by x of g at x plus the other term. So lots of parentheses there. Briefly, we normally just write x of f of g. X of fg is f times xg plus g times xf. Okay. And then there's the theorem, which is basically a piece of analysis, which is that any operator on smooth functions, Rn, which is additive and obeys this product rule, comes from a vector field on Rn. And that's not automatic. It does need to be proved. It's a bit of analysis. It's not seriously difficult, but it's not completely trivial either. And I'll give a reference for that in the printed materials. So I'll almost always move without comment between these 2 points of view. On the one hand, a vector field on Rn is a smooth map from Rn into Rn cross Rn. And on the other, for which the first component is the given variable, and on the other hand, a vector field is an operator on the smooth functions that obeys the product rule and is additive. There's a third point of view. Let's start a new page. There's a third point of view, and that's in terms of tangent vectors to curves. So if I go back to my original diagram and think of some curve, parameterized curve RT, passing through some particular point x, and there's its tangent vector, then let's say that that's t equals 0. Let's say that x is equal to r of 0. Then the derivative of r at 0 will will be, let's write it as x dot 1, 0, that's a dot, and x2 dot at 0. And if I write that in terms of the partial derivatives, then it'll be x1 dot 0 partial x1 plus x2 dot 0 at partial x2. And that's precisely what we get by composing, let's put in a function f. That's precisely what we get by composing f with r and differentiating at t equals 0. So this is showing that tangent vectors defined in terms of these partial derivatives are precisely the same as bound vectors and are precisely the same as differentiating with respect to along a curve in the plane. And all that's basically happening here is that if I differentiate a function f defined in a neighbourhood of x, then whether I go along the tangent vector or whether I go along the curve r, the derivative will be the same. And these 2 points of view, or these 3 points of view really, remain in place throughout manifold theory, and we'll deal with all of them from time to time. One last point. One last point about notation. One last point about notation. For x a vector field, that will be my standard notation. But x at a particular point and this of course is standard, but x lower x denotes an element of the tangent space. So if it's capital X, argument little x, then it's a vector field evaluated at little x. But this notation here, with the little x as a subscript, indicates that it's a single tangent vector at a single point, and that single point is little x. And it's regrettable, but it's true, that it's often, it's quite common to denote a single tangent vector as x also. This is potentially confusing. As you go on, you'll learn to spot it from the context, so it's not too much of a problem, but it's something to be aware of. Okay, that's all for now.